Okay, great. We're live. It's week 7. We're going to be talking about vectorization and functions. I'm still Breon, and it's November 10th. Is it really November 10th? Hold on. Goodness gracious. Okay. We have any questions before we get started on week 7 materials? So first, I wanted to start with a quick aside about approaching problems that are more than 1 or 2 lines of code necessarily. I'll start with saying that we should visualize our goals first. Before you can write effective code, you need to know exactly what you want the code to produce. The specific outcome that you want, exactly how long it's going to be, what the type of data is going to look like, and what kind of answers would be sort of in the realm of where you're going. You want to know exactly where it's going to be. So you'll want to ask yourself questions like, do I want a single value, perhaps a vector or a list? Do I want one observation per person? Or do I want my data to be something like person year or just the year? Most programming problems can be reduced to having an unclear idea of your end goal, or perhaps your beginning state. This is maybe one of the follies of our first few assignments, is that a lot of people have no idea what their end goal is as they're trying to shoot their shot on ggplots. And well, I might say, just shoot your shot anyway. A lot of the stress is that they can't quite figure out what their end goal is. If you know what you have, that is the data structure, and what you want, the outcome, the production, the intermediate steps are usually obvious. And getting there, you'll be able to start to say, that's a lot of work, but I know what steps to get there. When in doubt, sketch the beginning state and the intended end state. Then consider what translates the former into the latter in the least complicated way. Or write it out in a very complicated way. I'll give an example. If any of you came to my office hours yesterday morning, you will have seen, also, if that seems complex, translating your former into the latter, break it into more steps. But if you came to my office hours yesterday, then you will have seen this on my wonderful chalkboard. This is me following these steps. And I'll give you a quick explanation of what was going on in my data and why I had to write it down and why my brain doesn't want to sit with all these steps unless I write them down. So I have a bunch of information about businesses that opened in Los Angeles, okay? And what I have about that business is their address and who owns it and what's the name of the company and that it was born in LA at a certain date and that it died in LA in a certain date, okay? And I want to know more about this information or more about this business. And so I'm going to join it to another data set that has per year level information about businesses for the whole United States, okay? Now this presents a problem for me because that second data set is broken up into what we call time series cross-section data. That is, it's the year 2000, they have a bunch of data. Then they have another data set for the year 2001, and so on through 2020. But my original data set doesn't care about time. It just says the name of a business, when it was born, and when it died. And if I want to do some good modeling for that data, I can't leave it that way. And I also can't join them as is because I won't know which year in my cross-section time series to join to my birth years. You following? And so what I had to say was, okay, I have my birthday data, but what I want is the business year level for left joining to my employment data. Okay, so that's how I wrote it to myself. I'm just trying to motivate kind of what I'm talking about. And so what I had to do was get the distance from my start date to my end date in years. And then I made a data frame per business that was, each row was by the year. So let's say it was born in 2001, died in 2005. That's a 4 years difference. I now need that same row of data, but 4 times, one for each year that I was alive, so that I can join them back to each of my cross-section time series data. So I did that. I made a data frame per business, and then I input it using a for loop into lists with an element per business. And then I bound them all together so that I would have all of my data, but now instead of it just being one business with a birthday and an end day, it's now one business that was alive per year that it existed. And so this made my data set explode with the amount of rows that it had. And then the second part, I did this with a function, was I iterated over all of the dates in my bounds. So I would subset to the year. So I would just get, let's say, the year 2005, all of the rows that were for 2005, and then I joined them with that data that I had, the employment data, join that together. And I've iterated over all the years that I had until I got all of the rows for this data set to be joined with the time series. And I concatenated it all together. And now I get to run some really cool hazard models. But this is what I mean when I say a quick sketch, because if I was just going to look at this data and then look at this data, all of that is not going to come to me, and I'm going to forget, and I'm not going to remember all my steps, and yada, yada, yada.
How long that like whole big conceptual, like for you as a person that's like hours, like days?
To write this and make it, and make sure I had the requisite skill to do it, probably an hour. For it to run, about 12 hours.
And then what about conceptual?
To conceptualize it, I knew pretty quickly that this data, in order to fit into the model that I wanted, needed to be here. Probably about 20 minutes. But that was because I deal in event history models frequently, so I know what the data is supposed to look like. Okay, on to things that aren't as conceptual, what have you, into things that we're here for, which is learning R. So we're going to be talking today about vectorization and writing our own functions. So our example from last week was, remember we tried to find the mean for each variable in the Swiss data set, and we said, I don't want to type this out a bunch of times. Maybe we should do for loops. And then we settled on the best solution is actually to just use the column means function without even thinking about pre-allocation or any of that kind of thing for for loops. What were some of the other benefits that we had about vectorizing like this rather than using a for loop? Do you recall? Great. Yes, minimizing human error is a big one. Any others?
This one gives you like the column titles on each one.
It does. It does give you the column titles.
But you could write it.
You could write it into the loop, and it adds extra steps, right? For sure. Another one that comes to mind for me is the speed. That this runs a lot faster. Yeah. The speed is really important, particularly as we start to get into weirder data. But also just how quick it is to type call means relative to any of the other formats that we had. One thing I want to reiterate is that this also saves like human computation time. That when you vectorize things and you're like comfortable vectorizing, the amount of time that I had to spend thinking about making R run is a lot shorter than it is my time spent analyzing whether or not 70 for fertility means something valuable to society, right? Whether or not this is a good piece of research definitely trumps sort of the other things about how much time we spend messing around with R. So one thing I like to think about when it comes to vectorizing is how much more time it gives me, the researcher, to spend not thinking about how my data is constructed, but what these numbers mean and how we can get this piece of research to the right hands, you know? So vectorization avoids loops. We talked about loops last week, and we found that loops were very powerful and applicable in almost any situation. You could use them for basically any operation that you wanted to run over a set of things. However, they are often slower and require writing more code than vectorized commands. Whenever possible, use existing vectorized commands like the call means, or a lot of our dplyr functions are also vectorized in the same way. Sometimes no function exists to do what you need, so you'll be tempted to write a loop. This makes sense for a fast one-time operation on small data. But when you have lots and lots of data that you maybe need to calculate things for frequently, loops will get in your way. So earlier in this example, I used a loop, but I'm never going to return to this stage of my data analysis. This was just to get my data where it needed to be, and I'm never going to use that loop again. If your data are large or you're going to do it repeatedly, consider writing your own functions. It's not as scary as it sounds. I'll keep saying that until you believe me. Okay. Writing functions. Some examples of existing functions that we've been using are things like the mean, where we input a vector and it outputs a single number, or dplyr's filter, where we input a data frame and a logical condition of some kind, and it outputs a data frame with rows removed using those conditions. We also used the reader read_CSV function, where you input a file path and optionally variable names or types, and output a data frame containing info read in from that file. One thing to always keep in mind when it comes to R is that people wrote these. I think it's easy to forget that somebody like took the time to write down how read_CSV works and that we can check how they did it. So why write your own functions when fine people like whoever wrote read_CSV exist? Functions can encapsulate actions you might perform often, such as given a vector, compute some special summary statistics. Given a vector and a definition of invalid values, replace them all with NA. Perhaps you'd want a template for your favorite ggplots that are used in reports. Or maybe you want to define your own new logical operator. All of these things are kind of unique to your circumstances, and we'll probably not have a wrapped function that somebody else has already built for you. A few advanced function applications that are not going to be covered in this class, but if you'd like to know more about them, I'm happy to talk about them, are things like parallel processing, which is using more of the cores of your computer to run a calculation for you. It might not seem it, but R doesn't use that much of your computer. And you could make your computer spend more of its energy and computational power on R. That's what parallel processing is. You can make R generate other functions. It might not be necessarily clear right now why you might want to do this, but this is actually the way that dplyr works. And if you'll remember when we said like data equals dot, that's what's happening here. dplyr actually uses that dot to create another function that will run what you're asking it to do. You can also make custom packages containing your own functions. I've been playing around with this a lot recently, as my lady has been working late night on Saturdays, and it's just me at home by myself on Saturday. So that's what I'll be doing. There is actually a really great suite of packages for building your own packages in R. I'm happy to talk about that whenever, but those things are not necessarily covered in this class. We're going to be talking about functions that are more like these ones and less like these ones. Do we have any questions so far? Let's look at some functions then. So here's a simple function. Let's look at a function that takes a vector as an input and outputs a named vector of the first and last elements. So let me explain and break down what all is going on in here. First and last is going to be our new function. We're going to assign it. Here, this is the function. It makes functions. So here we say function x. X is going to be the thing that we can input to our first and last function. And then, like in for loops, we put the body of our function within these squiggly brackets. And the body of our function will do this. It will create a new object called first, and it will assign the subset of the first element of the input vector. It'll create an object called last and assign it the subset of the x vector at its length. So however long the vector is, this will be the last element of it. And then it will return a vector. So that's why we have, we're using the concatenate function here to return a vector that's named first, and that'll be the whatever object is here first. And then another element named last, which will be this last object that was created in the function. So let's see how it works. We can use first and last on a vector with the elements 4, 3, 1, 8. And the output will be first is 4 and last is 8. Question?
What's the difference between return and print?
Return is special for vector or for vectors, for functions, for saying this is what I want from the function to return. Like I want the function to output this. If you don't specify return, your function will give you the last thing that the function calculated, and that might not be what you want. Whereas print just takes information and puts it in the console. A couple of things to note are, first, people typically use x here as their input for a function. This is akin to in for loops, we typically use I, and then the nested we use J, and then that nest we use K. And also, when you run this command, it saves to your environment so that you can keep using it. So now we have our first and last function over here. And we can use it for things. But it saves here in your environment like anything else that gets assigned an object. Let's test our first and last function. What if I gave first and last a vector of length 1? So we just say first and last, the number 7. It will return a named vector with the elements first 7 and last 7. And note that it didn't kick us an error. It doesn't tell us anything. It just said, here you go. The first element and the last element are both 7. And this, of course, is not any different from a vector that was length 100, where the first element and last element were 7. This probably isn't what you want. It might be, but it's something to keep in mind. Or what if we give it something length 0? First and last actually kicks back an NA for something that doesn't have any length. Also, note that numeric 0 gives you a vector with no length. And if you start to really think about what a vector with no length means, your brain will hurt. Don't spend too much time on it. I'm sorry? If where I was working with character data, first and last. Let's see. My guess is it should. Cool.
So just keep it in order, not like an alphabetical or anything. Or that you put it in.
Yes, the first and last elements of the vector as it was given.
Why is it in quotation marks? Is that because you didn't have to put
Why are these output in quotation marks? Because it's maintained the same class as the vector that was input. So like if we said class okay, it's character. But when we had that other example, which I think was 4138, it's numeric. Okay. Maybe we want our function to be a little bit smarter so that it can deal with these kinds of strange cases. So we can check our inputs within functions using if-else statements. Let's make sure that we get an error message when the vector is too small. So one thing we could do is specify a new function. We're going to call it smarter first and last. And it's still going to be function x. And then in our squiggly brackets here, we're going to say if the length of x is equal to no length, something with length 0. This is the same as saying numeric 0. Having an integer 0 is something with no length. We can say stop. The input has no length. Else, run our function like it was before. So stop is a special case, sort of like return, that ceases the running of the function and prints the text inside of the error message. And you'll note in lots and lots and lots of all of the functions we've been working with, this is how you've been getting yelled at. when R Markdown is upset at you because you put install.packages inside of it, there is something in the R Markdown script that says this, and then gives that bunch of words that's nonsense to a human reader.
But for the homework where it, like, when we looked on it, you would tell us whether the answer was correct or not, you said you used loops for that one instead of a function. I think it's homework 4.
Yes, I'm trying to think where the loops were. They were a bunch of nested if else's saying, is this matrix the right dimensions? Is this data frame have the right materials inside?
So would you, is there a reason why you did that instead of this? Instead of making a function?
They were a function, sorry.
Oh, okay.
Yeah, they were called like test underscore X, I think. But this is how we might check our inputs for things. I typically, when I'm writing functions, only ever put 1 or 2 of such error messages. And that's because I don't write very complicated functions. It's hard to imagine setting yourself up for having a lot of different strange cases, such as zero length vector. I try to avoid that personally. Well, let's test our smarter function. We can use smarter first and last on numeric 0, our zero length vector, and it will return error in smarter first and last. The input has no length. And if we said smarter first and last, that same vector 4318, we'll get our same answer. Neat. Do you have any questions? We can crack open functions and see what's inside, which I said kind of in passing a little bit earlier. If you type a function name without any parentheses or arguments, you can see its contents. So here you could say smarter first and last, and these are the contents, the same things that we said earlier. You can also do this by putting your cursor over a function and hitting F2. I do want to note one sort of strange case. Let's say we do a dplyr filter, which we like. Filter is good. You'll see that it's maybe less instructive. It doesn't have as much content. It just says use method filter. That's because dplyr is, I don't want to say lying to you about what filter is doing, but what you want to do if you want to see sort of the underbelly is you would say dplyr, and then you'd use 3 colons, and this will give you all of the things that are inside of dplyr, including things that are hidden by things like use method filter. And so if we go down here to filter, what's typically happening is filter.tabledf when we use it for our everyday purposes. Oops. And we can actually start to see what's going on in that. It calls something dots. Maybe that's the data equals dot that you're used to seeing. And it has yet another proprietary function called compat lazy dots and filter dot data 3 exclamation points dots. And you can kind of just keep digging that way. And this is the point in the class where I revealed that a lot of the functions we've been working with are just kind of graphical user interface for you to get to these functions that are kind of deep down there underlying all of your regular functions. And when you start to get deeper down there, you'll realize you don't want those. You do want filter, and it's okay that it says use method filter, and we're not going to think about it anymore.
Does R ever, like, this sounds like there's functions layered on top of functions. When somebody submits a package, do they have to, are they allowed to have their package and their functions rely on other packages? Like,
Yes.
those first packages broke and then the whole screen, like, no effect.
Yep, that can happen. The best practice is actually, now that you've seen how this works, let's say that we look at our first and last again, but it's in a package that we like know and love. We can now just copy paste this and change it and then submit that as our function for our package. So that's what a lot of people do instead of nesting themselves within calling all these other packages, although some still do. And that's sort of what's going on when you say like library dplyr and it's saying like also loading this other package, is because it like needs them in order to make sure all of its regular functions that you see will work. Question?
Given what you started the class out with, I'm trying to understand the use of the validation area that you created for the smarter first and last. Can you like give an example of why you would want to do that, already knowing like what you're planning to execute?
Sure. So I had a function that was scraping a website for me. And I had a good idea about what 90% of the cases were going to be like when it was scraping, but 10% of them were kind of a question mark. And so I had a thing like this that would say, this one was weird, check on it later, right? And so it's like I knew what I wanted, but I still had like this sort of like ambiguity necessarily. Mm-hmm. Okay, so do you have any questions about cracking open functions? This one, I really like doing this just so you can steal other people's code. Let's say that you take a class called maximum likelihood estimation, and they're asking you to optimize a MLE for a model that was not described in the class. This is a really good way to make sure that you can do that using other people's code. For instance, let's say. So let's talk a little bit about the anatomy of a function. Functions have these parts. First is the name, which you assign to the function so that you can use it later. You can also have anonymous functions, which are functions that don't have a name. We'll see some more examples of that moving forward. Functions also take arguments. For instance, argument 1 here, argument 2. Sometimes these are called inputs or parameters. These are just the things that the user passes to the function that affect how it works. Things like passing x and na.rm to my new func. We could say set a default. You'll note that most of the functions that we use do already have defaults set and is actually part of the reason that we've run into errors before. Things like when we look at the help code for mean, here it says mean takes x. Also, trim is set to 0. We're all just cool with that being the default. And also, na.rm is set to false. as the default. The underlying code that makes mean run has this at this stage when the function's created, where na.rm is equal to false. And then when we say mean later, we can also specify that na.rm is equal to true, and that will change the way that the function uses our input. Next, we have the body of the function, and this is where all the calculation happens. And last, we have the return output. This will give us what our function is supposed to produce. As I said before, if you don't specify return, the last thing that will be created will be what your function outputs. And that might not be the thing that you want. Do we have any questions there? Is this making any sense? Okay, let's check out an example. Let's report some quantiles. Maybe you want to know more detailed quantile information than summary gives you, and with interpretable names. Here's a starting point. We'll make the quantile report function. We'll assign it function x, and we'll set as a default argument na.rm equals false. And then in the body of our function, we will specify quants and give it the quantile function, which also takes x and na.rm. Note that this x here is the same one in the body down here, not unlike our for loops, keeping that I and having it in the body of the function. You can make it do multiple things if you'd like. Also, whatever's given to na.rm is what this is. So if a user said true here instead of false, this value will read as true to the na.rm argument of the quantile function in the body of this function. Also, we've given to quantile an argument to its probs, or we've passed to its probs arguments a vector with a lot of different quantiles that we might feel like are interesting to our data analysis. And we've also provided some names to this vector that we created in here that are legible to us. And then we want it to return this quants vector. And now we can use our quantile report function on, say, 10,000 cases drawn from a random normal distribution. And here's what we'll get. How are we feeling about that? Are we cool how arguments are being passed down from the top part of the function to things on the inside? Is that tracking?
What would happen if you didn't have NARM equals false in the first argument?
It would take the default of the quantiles argument here, but we wouldn't be able to change it.
Yeah, so later on, you could use the quantile report. So this allows you to later on.
Right. Okay. I want to talk a little bit about apply functions. Apply functions are how I did that example from a chalkboard. Don't loop, apply yourself instead. Writing loops is challenging, particularly for new coders. Loops also require writing a lot of code and are harder to troubleshoot, I think, than writing your own function. But loops aren't the only way to iterate in R. Like a loop, apply functions iterates over elements of objects, except they don't need pre-allocation. So you don't have to like specify vector lists, length, however. You can directly assign the output. It also has the caveat that they must use a function. Nearly anything you can do with an explicit loop can be done more easily with the apply family of functions. Let's talk a little bit about how that's done today. One thing that we have available to us is the lapply function. This is lapply for list plus apply functions. Lapply is used to apply a function over a list of any kind. A data frame constitutes a list, if you'll recall week 4's lecture, and it will also return to us a list. This is a lot easier than preparing a for loop. So let's say we lapply our Swiss data set, and we're going to set our function equal to our quantile report, and it will give us a list of all of our quantile reports for each of the elements of the Swiss data frame, which is all of the columns. Very cool. It goes very fast. And you see that it's a lot easier than figuring out how I would write a for loop to write this quantile report. There's also sapply. This stands for simplifying lapply. A downside to lapply is that lists are often hard to work with. Sapply simplifies the output by making each element a column in a matrix. That's the usual case, I would say. See here, if we use sapply Swiss and send it the quantile report function, it has now recognized that all of the outputs have the same length and made them into a matrix with named rows and named columns. One thing I do want to note is that lapply, sapply, and apply are all base functions in R. There is a tidyverse version of all of these things that's in the purr package, P-U-R-R-R. I'm showing you these because these are more generalizable, but purr exists and you can check it out. It's cool. There's also the apply function, which has a little bit more flexibility, although is a little bit unwieldy. There is, it works over matrices or data frames or arrays. You can apply the function to each row by saying margin equals 1, or columns using margin equals 2. So we can say apply to the Swiss data set margin equals 2, which means for all of the column elements of our input Swiss data set, the function quantile report, and we'll receive back this matrix. I want to note that you can say margin equals 3. This is for the third dimension of an object. So if you had a bunch of stacked matrices, which are called an array, that's what you would use here. The numbers are corresponding to how you would subset things using the single brackets operator. So 1 being the first before the comma, 2 being the columns after this first comma, and 3 being in the case that you're working with 3-dimensional objects. But I reckon that if you're taking this class, there's probably not a lot of 3-dimensional objects that you're going to be working with regularly, but it exists. Maybe. You know, one time I was talking to this stats PhD who told me his research was about throwing a dart in 3-dimensional space and talking about the Bayesian probabilities of those things. And couldn't be me. Goodness, buddy. Okay. remember the loop for loading data files from last week? This is what we wrote. We had our dplyr and reader libraries. We said file list is our list of files in this particular directory. We created a bunch of file paths by pasting together the directory and the elements of the files, or the elements of the directory. We made names for all of these things by using the string remove function to get rid of the .csv from all of them so that they have nice names. We allocated a list so that we could iterate over it in the for loop. And then we also gave that list the same names so that the output would look nice. And we iterated over them. And remember, I was like, this is a very confusing thing and it's not necessarily how I'd write it. But we were able to get 10,000 some odd rows of data and stack them all together and make it look nice. If we use lapply, it would be faster and easier. We could just get our file paths, apply read.csv to all of them, and then bind rows. And we would get the same thing. And it would be faster. So I really like thinking in vectorized ways because thinking about how to write all of these things, particularly when you have weird nuances of your data, is not a good use of your human computation time. But if you can think of a way to vectorize it, you can spend your time analyzing the data rather than figuring out how to get it into your machine. Of course, the fastest and easiest way to use a fully vectorized data loading function, something like vroom vroom. We could just load library vroom and hand it our file paths data, and it would do all of that work by itself. Excuse me. Well, one thing to know about this is that it's just somebody else's apply functions. It is really fast though. It's faster than an apply function I could write. Okay, let's talk about how we might convert a for loop into an apply. So converting code in a loop to an apply function is pretty straightforward in the usual case. So what you're going to want to iterate over in a loop, say our sequence along X, will become the first input. Okay, so instead of having to sequence along, we would just say X. The body of the loop becomes a function. This function should take only the iterator index, I, as an input, and then assign the output of what your loop is stored values in. So here's a loop that we could use to think about this. We'll allocate a numeric vector, length 5, and then say for X and sequence along our loop vector. In our loop vec, for each element, give me X squared. And now our loop vec for 1 through 5, we'll say 1 X squared is, or 1 squared is 1, 2 squared is 2, or 2 squared is 4, and so on to 5. For this, we needed an empty loop or an empty vector to store our results. If we vectorize, we don't need any pre-allocation. We can just iterate over the numbers 1 through 5 and assign the output. So here we assign to the objects apply vec. We sapply our thing that we're iterating over, the numbers 1 through 5. and provide an anonymous function. Note that it doesn't have a name, just function x and then x squared, and we'll get the same results.
Wait, do you not have the return part of the function because you don't need it? It's so simple, it's just the one function, or is that a thing that's applied?
It's because of the simplicity of this function. Do we have any questions there? I will say that when I was a new R user, I liked to write things this way. This way made a lot more sense to me for probably the first couple years. Now this way is like, there's no going back for me. But now my data is a lot more complex and the questions I ask are weird. It does work. It works as well. I would just say that the allocation part gets clunky and weird a lot. And then what happens is because the allocation was weird, I just made it a list and now my list is kind of all over the place. And then I end up using an apply to make my list turn back into something useful. And then I'm like, well, I should have just written an apply at the start. Okay. So let's get back to making and using functions. Oh, one thing I did want to note here is that there are some processes where it doesn't, it's not that apply won't work. No, it is that apply won't work. Apply won't work in some things that are recursive. So like if you need it to iterate to the next thing and then remember what happened in the previous thing, sometimes applies, in order to make it do that, it's more effort than to just write a loop that does that. Because it's pretty easy in a loop to remember index -1 relative to trying to remember what's in between 1 and 2 here. Some examples that are maybe prescient to social scientists are MC methods. So Monte Carlo Markov chains. Is it Markov chain Monte Carlo? I don't know which MC is which, but those and some optimization processes when you're looking at the, what's the word I'm looking for? Convex hull of MLEs, and you don't have your global minimum. You want recursive things for that. But if you're into that kind of social science, you'll know that you want to write a loop. Okay, back to making and using functions. Okay, so here's an example. Discretizing continuous data. Maybe you want to bucket variables in your data into groups based on quantiles, right? So like income here, 8,000 and 12,000, we'll put in income bucket 1. And then these values are pretty similar, we'll put in bucket 2. And these values are pretty similar, we'll put in bucket 3. This is something that we do frequently as social scientists. Shout outs to Raj Chetty. I mean, I feel like all of his papers are just this. They're just doing math with these kinds of buckets. So let's make our own bucketing function. There's actually already a function in R called cut that does this, but you need to tell it what breaks, or in other words, what number of buckets to have. So let's make a function that calls cut using quantiles. I don't know what it was about this lecture that made quantiles sound like the thing to do. Using quantiles for splitting and returning integers. So we'll say to make a bucket function using the function. It'll take on x and its default quants argument are going to be 0.333 and 0.667. And then in the body of that function, we will create an object called new breaks, which are going to be the minimum value of our input vector minus 1. And the reason that we want to do this is so that we can contain our minimum value inside of a bucket instead of it being the boundary and losing our bottom case and our top case. Then we will call the quantiles function. We'll give it the x from up here, and the probabilities will be the things that we've given to quants. Here it defaults to 1/3 and 2/3. And we also have our max value plus 1 for the same reason that we had minimum value minus 1. And we will return our cut function, give it x, and our breaks are going to be equal to these new breaks that we've created. And we're also not going to give it labels because the labels are a little bit weird and making it into a factor. We don't necessarily need that. By default, this function will produce 3 buckets with anything below the 33rd percentile, anything from 33rd to 66.7, and anything above 66.7. Are we cool where this bucketing is happening and how it's going? Okay. Yep, that is something I said before. Okay, so we can try out bucket. Let's say we make some data that is 100 draws of a random normal distribution. We can also say that our quantiles of interest are 5%, 25%, 50, 75, and 95%. And then we'll create this object called bucketed data and assign it bucket with our data, which is this 100 draws. And our quants are going to be equal to dat quants, which is just this vector. And then we can plot it. I plotted it here in the base R plot because I think that it looks a little bit more straightforward for these purposes. But one thing to note about this is that we were able to overwrite our default quantiles that were given to our quants, right? This is not unlike when we had na.rm in that function earlier today. Do we have any other questions about bucket? Cool. Another example is, let's say we want to remove some bad data. Let's say we have data where impossible values occur. So different types of data, types of missing data are often coded this way in survey and administrative data sets, where they just seem like perhaps extreme values. So I've created some school data here. I made a data frame where school is equal to just an index for schools. And then I've created this vector, which is just some exam scores, and gotten a notion of maybe SES at the school by saying the percentage of students who get free lunch. And what we see already is that there are some values that are bad. Whether or not they're from the data collection stage or perhaps just the way that this data is coded, we probably want to get rid of those. Things like getting a negative 100% on an exam, or these 99s, or negative 13, I guess that would be negative 130% of students getting free lunch, that kind of thing. So to go back to the second slide, our goal is to have an input, which is a vector with a cutoff for low and a cutoff for high values in order to get rid of these bad values. And our output will be a vector with an NA in those extreme places. So we can make a remove extremes function, and we'll give to this function x, our input vector of interest, low and high, and we don't specify any defaults. This means that the function will require that we have these in order to run. And then inside, we'll just have an object called x no low, which is an if else statement, which is if x is less than our low value, give an NA, otherwise give the x value. Then we have x no low no high, which is if else x no low is greater than our high value, give us a missing otherwise the x value, and then return this object. And so we could say remove extremes, our school data, just our passing exam column, and specify that our low is 0 and our high is 1 because we're dealing with probabilities. And we'll get NAs for all of those bad values that we have. Do you have any questions there? I think I have one more example using the same function, but
Why was it just the exam and not the free and reduced price lunch?
that's what the next example is. We can actually combine this using dplyrs across helper function. We've already had some experience using across before, and it is just vectorizing analyses. So let's look at how it works. The dplyr across function allows us to apply a function to every variable to update the columns in the school data. So here we load library dplyr, we take the school data, and then we mutate across all of our columns that are not the school column. Because it takes the same kinds of arguments as select, we can use minus school to get rid of that column. And then here, this tilde basically means apply in your across setup in dplyr. So apply to the things that we are going to pipe to this function, our remove extremes function. X is going to be equal to dot, because it takes on that same sort of dplyr syntax of iterating over this dot. And then we set low to 0 and high to 1. And it runs and changes, it modifies all of our columns that are not the school column to get rid of all of our extreme values. Question?
Sorry, I might miss this. The dash and then this circle,
Yes, this tilde.
what are the significance of this?
The significance of this here,
That and then the dash.
the dash before the squiggle, this. Okay, so here, this is mutate across, says modify all of these things that I'm about to hand you. And then this says to mutate across everything except school. And then this says for everything except school, apply the remove extremes function. And then iterate over all of those columns that I'm about to hand you. Okay, are we cool there? A little bit about non-standard evaluation. dplyr uses what is called non-standard evaluation that lets you refer to naked variables. That is, variables that don't have any quotes around them, like school. So you'll see in this last example, school is a column in our data set, and it's specified just by writing school. We didn't say anything about it in quotes or backticks or anything. This is a little bit strange for people who are coming from other coding languages. dplyr verbs, like mutate, recently started supporting standard evaluation, allowing you to use quoted object names as well. This makes writing functions and loops with dplyr a lot easier by being able to say things like, give me the Swiss data set, and then select fertility and Catholic in quotes, and then show me the first two rows. And then it would know to grab these two columns. The reason that this is valuable to us who are learning how to deal with functions is that it's really hard to write a function that does non-standard evaluation, that lets you just write school and then have the function know that you mean the school column inside of the input vector that you're giving it, or the input that you're giving it. You can do it, but it takes a lot more squiggly brackets and a lot more computation time that you probably don't want to spend. So I just want to let you, make you aware of that and why some things are about to have quotes and not. Also, there are anonymous functions in dplyr, or that you can give to dplyr. You can skip naming your functions in dplyr if you're not going to use it again, right? Like when we had first and last, we could save it to our environment and use that function again. If we don't care to do that, we can just use an anonymous function. The code below will return the mean divided by the standard deviation for each variable in the Swiss data set. So here what's happening, we'll say Swiss, and then summarize across. And now this helper function, everything says summarize across all of the columns in our data set. Apply the mean, iterate over this dot, which means iterate over each of the columns that we're handing you. Divide that by the standard deviation, again, iterating over the columns that we're handing you, and remove all the NAs. We're going to have to specify that. And note that this isn't a named function because we're not going to use it again. And now it provides all of these values for us. Are we cool there? Do we see how this is like the anonymous functions we saw earlier when we were using the applies? I'm getting some iffy nods. I'll count that as a yes. Oh, great. Here is anonymous functions sent to lapply. So like with dplyr, you can use anonymous functions in lapply, but a difference is that you'll have to use the function part at the beginning. So rather in the dplyr version, you just say tilde and then can provide some sort of calculations. Here you'll need to say lapply Swiss function x, and then anything after that will be counted part of the function. You don't necessarily have to use the tildes or the curly brackets. You can just say mean x divided by standard deviation x, and it will provide the same values. And since it was lapply, it gave it back to us as a list. But these are equivalent ways of writing the same thing. I want to give a little bit of an extended example using ggplot talk about how we would write our own templates. Okay, sorry, I was checking the time, and then I was like, oh my goodness, we're 45 minutes late. Anyways, I want to talk about how to make things like a flexible ggplot. Let's say you have a particular way that you like your charts. So I'm going to use the Gapminder data to illustrate this point, and ggplot2. So let's say we have our ggplot data and we want to filter it to just Afghanistan. And our aesthetics are going to be on our x-axis is the year, and our y-axis is going to be our population in millions. And we'll make our line the color red or fire brick with no x label, and our y label is going to be population in millions. With the GG title, we like the minimal theme and the title to be big. Cool. So the question then becomes, how can we make this flexible for any country? If you were going to write a function that did this, what would you change? Country, how so? Right, like you would make this an object, and then you could sub out that object in your function. Exactly right. How could we make this flexible for any Gapminder variable? So instead of, say, population, we want life expectancy. That one's going to be a little bit weirder. Let's see. So here's an example of the desired chart that we want. This was, in fact, the example that we had, where we have the population of Afghanistan since 1952. On the y-axis, our population in millions. On the x-axis, time. But maybe we also want the same function to be able to produce this plot, the life expectancy in Peru since 1952. So let's talk about how to make our country flexible. We can have the user input a character string for country. I'm changing the name here so that it's a little bit more legible instead of like that na.rm example. Country with no vowels as an argument to the function to get subsetting and the title right. So here we would say Gapminder life plot. We're making a function where the input is a country. And then the body of our function will be a ggplot where we take the Gapminder data and then filter to our country is equal to whatever country we're inputting. And then our aesthetics are still time on the x-axis, life expectancy on the y-axis. Same geom line, we're still into the same theme minimal and that kind of thing. And then we'll pass to GG title. We'll paste life expectancy in, and then our country input, and then since 1952, and keep this same big title. And so here, country is doing two things. It's going to be the filter, so our specific value, and add text in our plot. And so, question? No, you got it.
I'm trying to understand, so you went from population to life expectancy and you asked us how you can switch the variable?
We'll get to that example.
Okay,
Yeah, no, you good. So for our Gapminder life plot, we can enter our country is equal to Turkey, and it will just give us a plot of Turkey and change the title. Or we can change it to Rwanda, and it will just give us the country and the title. We're going to need a little bit more markup if we're going to make our y-axis a little bit more flexible. So now let's say that now let's allow the user to say which variable they want on the y-axis. How we can get the right labels for the axis and title. How can we get the right labels for the axis and title? Came out weird. We can use a named character vector to serve as a lookup table inside the function. lookup tables are really important for things like this, but also if you're into making like shiny apps, which is like R's way of being able to make interactable plots and things with drop-down menus and what have you. There's an example of one on my GitHub, if you'd like to see. But here what we'll do is specify a y-axis label. And what we'll need to do is make a named vector. So here our names are equal to the same things as the columns that we might want for our y-axis. And then what the underlying part of the vector is going to be for the y-axis label is going to be all of these things. And then for our title text, again, we want our names to be the same as our variables that we might use. And then the elements of the vector to be things like life expectancy in, population of, GDP per capita in. And then we can subset things in our y-axis label to by our column names. So we could subset by pop and get population millions, or our title text subset by pop, we'll get population of. Question?
And my follow-up is, while this seems to some degree fast, it doesn't seem efficient because you have so much data in Gapminder, country data. So is this just one sort of function that is not as fast as you've shown with other examples?
I think that this would be the faster way to do it if you wanted people to be able to interact with it. So like if you can imagine that they had to drop down and select a country and then select life expectancy, this would be the fastest way to do it. Because there isn't once this part is like long-winded, but it's way less long-winded than writing a plot per each configuration of all of the combinations, right? Next, we'll make our Gapminder plot function. And in it, we'll call it Gapminder plot. Oh, sorry. So ggplot is usually looking for naked variables. Like I said before, it does non-standard evaluation. But we can tell it to take them as quoted strings. This is standard evaluation using the AES string function. This is instead of AES, which does non-standard evaluation. This does standard evaluation. This is handy when you're making functions because, again, it's a lot more complicated for you yourself to write something that does non-standard evaluation. So our Gapminder plot function is a function that will take on the country and y bar inputs. We will put our lookup tables in here, and they will be subset by whatever is given to y var. And our title text is also going to be subset by whatever is given to y var. So it will subset by pop if people give it pop, subset by life expectancy if people give life expectancy, and so on. Oops. And then in our function, we'll create our same ggplot. We're going to filter our country is equal to our country input, and then mutate pop equals pop in millions. And we can just leave that in there because even if they don't use population in millions or don't use the pop thing, we still want it to be an available option if they do decide to switch and use pop. And then our AES string says x is equal to year in quotes, y is equal to our y var, which when given to our function will be life expectancy or pop or GDP per cap with our same line with the color that we like. And then our GG title will equal our title text, our country, and then since 1952. We could have also made this flexible for the same ways that this is, but I feel like that was getting to be even more long-winded. With our same labeling practices that we liked from before. And now we could say gapminder plot, country equals Turkey, y var equals population. We could say country equals Rwanda, y var equals GDP per capita, and so on and so on. And it's really flexible and can handle all of our configurations of y variables and countries. So are we cool there? Question?
So, I think one of the things that I got stuck on is how in the earlier description of how you were going to show the by different country here, I didn't see the brackets. I don't see it being like vectorized.
Okay.
It just seemed like you were writing code that you would just repeat, but now.
Okay, you good? Thank you. Yes.
So in this situation, you're saying to be any of these choices.
Yes. Yes.
Why wouldn't it,
Cool. Our last thing I think we're going to cover, I can't remember what the last couple slides are about. So we'll see them when we get there. We're going to talk about making an operator. One problem that a lot of people run into is what is the opposite of percent and percent? Oh, R doesn't have one. So if you'll recall, percent and percent returns true, where elements on the left are equal to any element on the right. So let's say we make a vector called USCA, which is just Canada and the United States. And we want the gapminder data and then filter country is percent and percent USCA. And then distinct country and then the first two rows. And we'll see that it's subset to the things in our USCA vector, right? But it's not very obvious the way that you would flip that to make it that we don't want just Canada and the United States. We want everything but Canada and the United States. The way that you're supposed to do it is maybe a little bit clunky to my brain. I don't know if it is to yours, to say gapminder and then filter not country, percent and percent USCA, and then distinct country first two rows. And we see that we're on the right track. We have everything but the US and Canada. I think that this is not a good way to write this. My brain says not this country column. It's unintuitive to me. So let's say I wanted to write my own operator. We'll call it percent, not in percent. We can invert or negate percent and percent to get a not in operator. So we could say percent, not in percent, and this is in backticks. Because you'll remember backticks is how we can make our operators perform like functions. And we can assign to it, negate our percent in percent. So in this example, we could say gapminder and then filter country percent, not in percent, USCA, and then distinct country, the first two rows, and it has gotten rid of it. Negate is a little bit confusing to read about, but this is how you would do that if you're ever in trouble. Are we cool there? And if we wanted to write other operators, we would also put them in backticks the same format. Okay. Wrapping up. A bit about debugging if you're used to, sorry, if you're used to other languages, perhaps. I'm laughing to myself because there's a thing in Tekken. Don't worry about it. I'm sorry. It's called debug. It's really fun. Okay, there's a character in Tekken who's in all of the Tekken games, like since like '92, whose name is Jack, and he has a move that's called debug, and you always are supposed to say it like debug, and so like when I read this, I went in my brain, but then it was inappropriate for me to say debug.
That's a bro culture.
I know. Tekken's a great game. Highly recommend. Anyways, if something's not working as you hoped in the function that you've written, you can debug it. Try using the debug function on a function, which will show you the world as perceived from inside the function. So you can say debug gapminder plot. And then when you fix your problem, you can use undebug on your gapminder plot or whatever function you are trying to debug so that you won't go into debug mode every time you run it. Let me see if I can debug, what was it, first and last? Okay. And so it'll show you step by step what all the things are. I don't tend to do this, so I'm getting very confused right now about what's going on. Oh, I meant to say undebug. Okay, I'm getting very confused. I need to go. All right. I think that it's because something about where the function was coming from was a miss, and because it's not a very, there aren't a lot of things going on in that function. But, I want to review the process. So data processing can be very complicated with many valid ways of accomplishing it. I believe the best general approach is the following. One, look carefully at the starting data to figure out what you can get from them. I think a lot of people run into the problem of maybe overestimating what their data can tell them, or underestimating what some variables can contain. Number two, determine precisely what you want your end product to look like. And I mean like exactly. If you want something to be a percentage, build that into part of the process. Don't just leave it as a percentile or what have you. Knowing that you want a percentage and not a percentile, invaluable information for making sure that your numbers are coming out how you want. Identify the individual steps needed to go from step 1 to step 2 and be like grossly specific about what all needs to happen between steps 1 and 2. Make each discrete step its own set of functions or function calls. If any step is confusing or complicated, break it into yet more steps. And 5, and this one's very important, complete each step separately and in order. And then do not continue until a step is producing precisely what you need for the next step. Do not worry about combining the steps for efficiency until everything works. I see a lot of people who run into this problem in data pipelines who just want to make sure that the pipeline is all there, and then step 4 out of a dozen breaks. And then it doesn't make sense why you wrote 5 through 12, you know? Once finished, if you need to do this again, convert the prior steps into functions. One bonus function, my lectures are rendered with a function. I render and print the slides this way. This one's a little bit old now, so it's not necessarily exactly like this, but what happens here is this render and print slides function, I just call and it takes them all together and puts them where they need to go in my GitHub. And then I just go through and add the links so that you can see them on the website. But it will take the directory using Git working directory and paste it together with the week of the lecture. And then it will look at the markdowns within that week's directory. It will knit that markdown. It will then look at the HTML version and create some space for PDFs and R scripts. It will tell me that the slides are then rendered and that I should wait 5 seconds. The computer will then wait for 5 seconds. And the reason is that the things as they rendered don't necessarily aren't done for a little bit. Then it produces a message, purling slides, which is to say that it is taking the information and making it available to other things. And then it does a headless version of Chrome. So Chrome opens on my computer, but with no window, and looks at the HTML version of the slides and then prints them as a PDF. And then it says, these are done. That's more or less how they're still done. I think it's cool. For your homework, the last one. Yeah, because 7's optional. So 6 is broken up into 2 parts, but it is the last one, unless you do the optional. You're going to download and analyze data from the first year of Seattle's Pronto bike sharing program. You're probably saying to yourself, Pronto bikes? I don't know what that is. They're gone. There was a data challenge. Maybe my first year I lived here. My first year of grad school, like 2017 maybe. That was like, tell us what went wrong with the Pronto bikes. But using the provided template that's on the course website, you will write a loop or lapply if you'd like to read in the data from multiple files. Don't just use Vroom. You're also going to write some functions to clean up the data and a function to visualize ridership over the first year. There is some string processing needed, much of which will have already been seen, or you can probably Google. But some of that will come in next week's lecture. I give suggestions in the template, but I can cover string processing in detail in the lab if needed before the homework is due. I think that we've had exposure to all of the things that you'll need, like substring and some of the stringer functions that I've used in the class so far. Part 1 is due next week. Part 2 is due in 2 weeks. I also wanted to show it and make sure that we're on the same page with everything, because I'm realizing as I'm talking out loud right now that this folder that you need in order to do the homework, I don't think I have a link for it on the course website at the time of this recording, but it is available here and on the end of the slides. I will make it available to you. The folder containing about 900 megabytes of files. And trying to think if there's anything I want to warn you about at this stage. Oh, the original writer of this class, Rebecca Farrell, a legend in her own right, made this data downloading demo that is a dark, depressing journey about data hell. That's loosely based on the thing that's also available on the class website, The R Inferno by Patrick Burns, which is also a really great read. Highly recommend both of those if you've got time. Although at this point in the quarter, I don't think you do.